Hello, my name is Edo Liberty. I'm the founder and CEO of Pinecone, and I want to tell you a little bit about the rise of vector data. The first thing we need to talk about is what do we do? What does our brain do when we see things, when we identify objects, when we look at our loved ones? I would say there are two conceptual, very distinct components of that process. The first is almost mechanical in a sense. Light hits your retina. Your retina is the equivalent of a CCD in your camera. That's what records. Those are the rods and the cones that actually record the light intensity. That is translated to neural activation, which is passed backwards to your visual cortex. The visual cortex is in the back of your neck. Has several different layers that translate that optic signal into a neural signal by deeper and deeper layer of neural translation. At the first layer, translating nearby signals and understanding things like edges. In V2, things that have to do with curvature already. In V3, you already start to be able to see activations of neurons that have deeper contours and shading and so on. And the deeper you go into the visual cortex, the higher and higher level of presentation of those of the visual signal is available. This is incredibly similar to how convolutional neural nets actually process the world. Once you have that neural activation, once you have that vectorized version of the image, which bears very little resemblance or any resemblance to the original image, like the optical image, that is transferred to other parts in the brain, mostly the temporal lobe, where things that have to do with object recognition, face recognition, memory, and so on, visual memory, and so on, are executed. And so those higher, the point of the slide is to say that the higher levels or the higher functions that have to do with vision actually happen on an object that has very little bearing to the original intensity of the light that hit your eye, but rather on the very rich representation that is the output of your visual cortex. So everything you remember, everything that you identify, and everything that you look at, in fact, are those high-dimensional representations and not the original image. I want to say that I'm telling you this because this is exactly how machine learning does this today on a very wide variety of topics. So first of all, of course, in images, we have convolutional neural nets and other types of neural nets nowadays that are able to take an image and transform it to its vector semantic representation. And once we have that, we can branch to higher cognitive functions, such as the duplication and similarity search, product search in the domain of retail, scene detection, and so on. But that is not limited to text, to images. It's how we process text nowadays as well. We take long pieces of text with transforms, with LSTM models, other language models. We are able to embed them into vector space such that we can do language understanding, sentiment analysis, question answering, semantic search, and so on. And again, perform these higher cognitive functions over the deep semantic vectorial representations of text. The same thing is true for audio, but this extends also to user behavior, to a whole set of other, a wide set of other sources of data. In fact, these models that would function as the visual cortex or the counterpart of the visual cortex for text, for audio, for video are already pretty commonplace. If you're using any one of those, any one of the common deep learning frameworks like MXNet or TensorFlow or PyTorch or Caffe and so on, you would have access to pre-trained models that are widely available. Things like ResNet, AlexNet, VGG, SqueezeNet, DenseNet, Inception, GoogleNet, MobileNet, and so on for vision, BERT, and DistilBERT, Word2Vec, and others. It's the list continues, and new ones are being trained and made public on, almost like a weekly basis now, maybe even a daily basis. In fact, they are so common nowadays, and they're so easy to get that literally with 2 lines of code in Python, you can import Torch Vision, and from Torch Vision already load, for example, SqueezeNet, which we'll see later in a demo how we use that. And so the component of converting the raw the raw input to its vectorial neural representation, that part is fairly available and easy to do nowadays. The question we want to ask ourselves is, what happens if we save all these vectors? What happens if we now aggregate millions or billions of these semantically rich vectors? What higher cognitive functions can we enable on top of those as a system? And so I think that the obvious thing that you would try to do, or the immediate thing you would try to do, is recognize objects, or at the very least provide the ability to measure similarity and retrieve things that you've already seen. That means taking that very large collection of objects and just return the most similar items or the most semantically relevant items in your collection. And so if that is embedding, for example, images of shoes, you might, first of all, detect to begin with that those are shoes at all, but then, their color, their shape, their brand, their style, and so on, all should be encoded in that vector somehow. And you can measure distances differently such that you retrieve the set that you're interested in. What I'm saying isn't new. In fact, you've experienced and used those services, used such technologies before. If you searched on Google or Bing, you've used NLP models that convert your queries to high-dimensional vectors and search through documents that way to search for relevant documents. If you've shopped on eBay or Amazon, you have been recommended items based on your personal based on the way that Amazon and eBay have embedded you and your behavior as a set of preferences, and likewise the items in their catalogs. If you listen to music on Spotify or view images on Pinterest, the same thing happens. You're recommended items based on their deep embeddings. And if you're using LinkedIn or Facebook, your feed ranking is organized and sorted based on preference, based on those kinds of embeddings and deep understandings of those pieces of content and your preference. Why is this reserved to these large players, and why isn't everybody doing this? And I think it comes down to the fact that that serving these models in production requires a very different kind of infrastructure. And I would say that if you have a key value store, then that is like pairs keys and values mostly, and you pretty much know how to do that. There are great tools for that. You have data structures, databases that essentially search engines that map documents to terms, and so you can search for specific terms or specific filters and retrieve the relevant documents. There are graph databases now taking hold. They existed for a while, but they mainly care about the relationships and facets of objects and the relationships between them. And I want to say that vector databases are a whole new different kind of infrastructure that takes these high-dimensional vectors and is mostly concerned with their geometric relationships, their proximity and angles between them, and so on, which is very, very much needed for these types of machine learning workloads. So why is this a new database? Why is this hard to do? I want to say that when you're looking at high-dimensional vectors, or vectors in general, those are not attributes or terms. They're not discrete objects. They're numerical values. Numerical values have present challenges in and of themselves. If you're looking for example, nearest neighbors or anything that's within the red circle on the left, and you think about those dots as two-dimensional vectors or pairs of numbers like x and y's axis, then you can imagine being able to dissect the space in a way that you can say a priori, the red circle only intersects the gray rectangles, and maybe I should look only in there. And your intuition will be absolutely correct in 2 dimensions. And that you would have discovered an algorithm called KD trees that's been known for a very long time. In high dimensions, however, that does not work. And the space actually looks a lot more like what's happening on the right-hand side, where the red area, or like a cap, which would be the analog to a circle in 2 dimension, is very likely to contain no points, or very few points. And pretty much all the other points are going to be very far away from you. So if your cap is in the North Pole, almost all the data is going to be around the equator and create like very numerically challenging retrieval algorithm. That is that fact is corroborated by the fact that there are tens of algorithms and open source libraries that are dedicated to solving this problem efficiently. They trade off speed and accuracy. And each one of those libraries has several different algorithms usually, and each one of those algorithms has many different parameters, and each one of those excels and does better than others for different data sets. There is a website called ANN Benchmarks that allows you to actually, that's not the website itself, but it's a piece of software that allows you to measure performance of one library against another in different settings. More than that, your difficulties don't stop there. Once you've figured out the index and the algorithm and all the parameters, and you've figured out, all the different trade-offs you need to figure out, you have to build a very large system around it. First of all, you're missing key functionality that allows you to operate those things in production. You need to start sharding and replication to be able to even scale to the volume of data that you have and the amount of queries per second that you might be seeing. But you need live updates. So the second you update a query, update a vector, it will immediately be reflected in the index. You need all sorts of advanced features like namespacing and arbitrary filtering that allows you to make sure that you're not presenting the wrong content to the wrong person. And you need to facilitate all the pre and post processing that in this case happen to be machine learning models. So now your system also has to orchestrate that as well, and all the connections in and out of that distributed system. And that is a significant undertaking. More than that, you'd have to take it to production. And so you'll have to care about high availability and persistence and consistency. You'll have to care about monitoring and alerting and supporting your service. And so these end up being significant undertakings that very large companies can allow themselves to take, but medium and small companies just don't. At Pinecone, we wondered how much can we accelerate this trend? How many higher cognitive functions can we allow medium and small companies by taking all of that and making it a managed service? And I want to say that I think we have made significant progress, and I think we've made this significantly easier, and we are able to now unleash a lot of capability and enable a lot of different use cases in different companies. In the following example, I would go through how to produce an image search application with Pinecone. Now we'll see a demo on how to build an image search application with Pinecone. The idea is to take a large collection of images here on the right, take a query image, maybe like this seagull, and look for other gulls or other birds in your data, in your set of images. To do that, I'll go to Pinecone's website. I'll put in my first, last name, and email and get an API key. I've already done that, so I don't need to do that. Once you get the API key, you'll get an email within a few minutes, and you'll be able to use that in the service. I can scroll down to start my image search example, or I can look at it in the docs, in the example section, or in the learn section. But you could just go off of the main website as well. I'll just click on image search. You have it in blog form if you're interested, or you can click on the Colab link and open it as a Google Colab that you can run yourself after you put in your API key. Here, I'm actually switching to the Google AI platform and running it on my own GCP instance with a notebook, with a managed notebook. It's the same exact notebook that you would be running in your Colab environment. What we'll see here is like an 8-step process. We'll install some dependencies, download a data set called TinyImageNet. We'll download a pre-trained computer vision model for transforming images to vectors. We'll use that to actually transform the images to vectors. We'll create an index. We'll upload and index all the images in vector form to Pinecone, and then we'll perform some queries, look at results, and delete the index. So without further ado, let's install some dependencies. Here I'm installing the Python client. I'm upgrading my pip install just in case. I'm installing Torch Vision, Pandas, and Matplotlib for showing some stuff. That is done. Here I have to put in my API key, which I have. And so I'll copy it. Give me 1 second. Here it is. And so now I have imported Pinecone and I've initialized my client, and I can run now as an authorized user. Here I'm just confirming that the versions match. You don't have to do it every time. Here I'm downloading tiny ImageNet. This is not a very large data set, and the GCP connection is very fast. And so I have, I think actually I've already pre-downloaded those to this instance, and so that is pretty quick. I just check that the files are there, but it usually takes, you know, maybe 10, 20, 30 seconds. Here, now that I have the data, I can use Torch Vision. It has a nice utility that lets me iterate over the folder structure and create a flat list of data, of file names and labels based on the folder structure. And now we can look at those images. And so this is, these are just utility functions that print images to the screen. And this is, you know, an image not unlike the one we saw before. Just a collection of those, like some food, some basketball, some corals, and so on. So this is a sample from our data set. We have, I maybe did not mention it, the data set is 100,000 training images across 200 classes, 500 images from each class. Now we need to create a model that transforms images to their embeddings, their vectors. To that we're using PyTorch. And specifically inside with PyTorch, we'll use PyTorch to download a pre-trained version of SqueezeNet. For each image, we'll perform some rudimentary normalization and then apply the model here. And so this class now downloaded this model and created a class that is able to transform images. Now I need to actually transform the images, and that takes a few, maybe like a minute or two. Note that this instance needs to now apply this model for every image in my data and create this vector embedding. I note that it's possible to actually give Pinecone the models themselves and have Pinecone be in charge of this step, but it's more involved, and I think it's outside of the scope of this demo. And I think kind of the main idea is already shown through already converting the vectors and uploading the actual vectors to Pinecone. We should be done with this fairly quickly. Here we're only using 2,500 images for this example. What we'll do later while this is running, we will split the data as 90-10. So what is like 2,250? Am I doing this correctly? Points, images are going to be in my corpus. So these are going to be using my data. And I'm going to use 250 images as queries. Okay, so this is what this split does. We'll run that in a second. And then we'll create an index. And so here I'm just naming my index. This is the first time I'm actually using Pinecone. I'm just creating a string. This is the name of my index. I make sure that the index doesn't already exist. If I'm trying to create an index that already exists, it will throw an error. And here I'm creating the index. I'm telling the name of I'm giving Pinecone the name of the index. Here it says you should use Euclidean distance as the measure of similarity. So closer means more similar. And it's a relatively small index, and so I can use one shard. You can use more shards if your data is larger. You can use replication if you need a higher QPS and so on. We're not going to go into that here. So this cell is now finished. I can now run this. Just look at my data frame. My IDs are just the names of the files on my local hard drive, and the embeddings are these vectors. And so now I can split the data, and let me create the Pinecone service. This should take only a few seconds. All right, so now we have a managed service, a vector index on the Pinecone side. This is a remote service, of course. This isn't happening on this machine. And so for me to connect to it, I have to create a connection, which I'll just call index. Mind you, the index itself is, again, as a channel, as a connection. It isn't the object itself. It isn't the index itself. And here I'm upserting. So look, I'm creating index.upsert. And what it gets is a list of tuples, being the IDs as the first object, the first item in the tuple, and the vector is the second item in the tuple. And this is just an iterator over those. So here I'm running the upsert. Note that it was incredibly fast. So Pinecone already ingested and indexed 2,250 vector embeddings corresponding to my images and their corresponding IDs. Look, now I have 250 queries that I would like to issue. Here I'm going to run those queries as a batch, batches of size 100. So that would be 3 query requests. I'll time it just so we can see what we get out of it. And here I'm getting a throughput of about 1,000 items per second, 1,000 queries per second. This, I want to stress that this is highly dependent on the network you're operating from. If you're in some place random on the cloud, it might be that, it might be slightly lower, might be slightly higher. If you're operating on a Google Colab or some less performant environment, it might be lower, and on your laptop at home, this would be quite significantly lower. Most services actually do what's called unary calls, and so these do queries one by one. And that is, of course, significantly slower because this is not batch, and so I actually have to do a round trip of communication for every query. We see that we only get about 50 queries per second in this setting. Finally, it's time to actually look at the results. To do that, we'll just print the relevant queries and then the images corresponding to the result set. And so for gulls, we get mainly gulls. For corals, we get mostly corals. This is jellyfish, food, etc. I'm sure I can find somewhere where this isn't perfect. Here for something frying in a pan, you get this what seems to be taxidermied bird. Or is it alive? I don't know. Anyway, so these are results for image search. Note that some of these images have, this image of a gull, for example. The first one is very different than this last image of a gull. And so the comparison isn't done pixel-wise. It's done a much deeper semantic level for the comparison of those images. Finally, when I'm done with my service, obviously if this is running in production, I would leave that on. If this is just a tutorial for me and I'm done, I can just delete the index and free all the resources associated with it. And once I'm done with doing that, I'm not using any resources on the Pinecone side, and there's no service waiting to be answering questions, answering queries. That is it. Thank you very much. I suggest you go to Pinecone.io and look at the examples and tutorials. I'm sure you'll find something that you would like to try to do. Thank you so much.